Hello guys, welcome back to Maths Zone African Motives. Still on our power machines N5 revisions, working on the heat value together with the combustion of fuels by mass or by volume, but specifically focusing on the heat values in this case, or the calorific values of given fuels. All right, so we are given a question from our November 2019 question paper, where we are given the composite of a sample of fuel according to mass. So this was taken by mass, is given carbon, hydrogen, sulfur, and oxygen. Then the calorific values are as follows for carbon, hydrogen, and sulfur. Then the vapor pressure is 5 kilopascal, that is the pressure is affected at 5 kilopascal. Then we are asked to calculate from this information 6.1 the higher heat value of the fuel in megajoules per kg. All right, so if we are to check our information from what we have, the percentages and so forth, they're supposed to work with these percentages, all right, and to calculate the higher heat value, which is in this case is referred to as the higher calorific value. That is, we are simply calculating the higher calorific value. So checking from your formula sheet, this part you're not supposed to worry because you are given two formulas to calculate, one for the higher heat value, which is the higher calorific value, and the lower calorific value, which is from these two formulas that we are going to consider. So if we are to check from this formula, we're given the calorific value, which is the heat value for carbon, the heat value for hydrogen, the heat value for sulfur, together with their corresponding percentages. In this case, the ones that we are given, these are the corresponding percentages. All right, so I'm going to take the formula, like I said, the one that we are going to consider because we are to calculate the higher heat value. So as we saw from our formula, it is given by the calorific value for carbon times the percentage of carbon in this case, plus the calorific value for hydrogen in this case, into H2 minus O2 over 8 in this case, all right, which is the percentage of hydrogen, percentage of oxygen, plus the calorific value for sulfur times sulfur, which is the percentage of sulfur in this case. So with this formula, we can obtain the higher heat value, which is the higher calorific value, as we are given the corresponding calorific value for each for carbon, and also the percentage corresponding to carbon from this, the percentage of carbon, that's 85%. Since the answer is needed in megajoule per kg, we are going to use these values in megajoule per kg, all right? So that means in this case for carbon, that's 34 megajoules times the percentage of carbon. So we are going to have 34 in this case times the percentage of carbon, which is 85%, that's 0.85 percent. All right, sorry for that. This is 0.85% plus the calorific value for hydrogen. Also, we are given in megajoules for hydrogen. That is 142. The percentage for hydrogen, 7%. So it's 142 times 7%. So we are going to have a 142, sorry, into hydrogen, which is 7%. That's 0.07 minus oxygen, as part of water. We are going to need oxygen, the percentage of oxygen, which is 2%. That's 0.02 if we divide by 100 over 8 in this case, all right? Plus the calorific value for sulfur. For sulfur, that's 9 mega joules per kg, times the percentage of sulfur, which is 6%. That's 0.06 as a decimal. So this whole part is going to give us the higher heat value. So you can simplify each and every part if you want. You can simplify each and every part, or you can just give the answer at the end. So if we are to simplify each and every part here, this is going to give us 28.9 plus here we are going to obtain 9.585. Then for the last part of sulfur, it is going to be 0.54 in this case. All right, so that's our higher calorific value, which is the higher heat value in this case, is going to be given as 39.025, which is in megajoules per kg. Since these values were in megajoules per kgs, so meaning to say our answer also is going to be in megajoules per kg. So that was the first part of our question. Then the second part, it was to calculate or to determine the lower heat value of the fuel in megajoule per kg again. So the lower heat value, as we saw the lower calorific value, we are also having the formula corresponding to this part, which is the lower calorific value or the lower heat value, which is taken from our formula. So this is given as the higher heat value minus HFG, which is the latent heat in this case. So we are considering our latent heat into 9H2, which is the percentage of hydrogen percentage. This is the higher heat value, sorry, the one that we got in megajoules per kg. So meaning to say also your latent heat must be converted to megajoule per kg in this case, all right? So let us check, let us have our formula, then we shall talk about this from our values that you're given. So as you can see, we said you're gonna have higher heat value, which is the higher calorific value minus the latent heat into 9H2 like this. So if you are given the latent heat, therefore you're simply gonna use it. Mostly they can give you the latent heat in kilojoules per kg. Convert that to megajoules. You simply have to divide by 1,000. It will be in megajoules per kg in this case. All right. But in this case, if you check, we do not have that value. We are not given anything about the latent heat, but we are given that all this, the vapor pressure is at 5 kilopascal. So we can have the latent heat, which is our HFG, at a given pressure of 5 kilopascal. What is going to be your HFG at that point, which is the latent heat in this case? So if we are to check from our steam table, let us check here from our steam table at 5 kilopascal under pressure. So we are going to need your values under the pressure. Remember, the pressure here is in kilopascal. So we are going to take 5 as it is already in kilopascal. So this is the part that is corresponding to 5, in this case, 5 kilopascal. This whole part here as it is. All right. So as we are not focusing with the whole part, we are only focusing on 5 kilopascal, but under the latent heat, which is given as HFG, which is measured in kilojoule per kg, and the value there is 2,424. So we are going to have this value at 5 kilopascal. We said our value is going to be 2,424 kilojoules in this case per kg. All right. So as we have got this value in megajoules per kg, it means we are supposed to convert also this to megajoules. So like I said, we divide by 1,000 to convert to megajoules. So if you divide by 1,000, that was going to be 2,424, which is now in megajoules per watt per kg. So that is it. We can substitute our values, everything. We have got everything in this case. So our lower heat value, the lower calorific value is going to be the heat, the higher heat value of 39, the one that we got previous, which was 39,025 megajoules per kg, minus the latent heat in this case. Like I said, this is our latent heat in this case, all right, which is 2,424. It's already in megajoules per kg, so meaning to say it can be corresponded to this part. So this is 24, all right, times 9 times the percentage of hydrogen in this case. So there we need the percentage of hydrogen. From our information, hydrogen has got 7%. So that's 0,07, the percentage of hydrogen there, 0,07. So that was going to give us the lower heat value, which was going to be 37,498 megajoules per kg in this case. All right, that is per kg fuel. That is how we play around with this information. If we are given, sometimes you are not given the pressure direct. I mean, sometimes you are not given the latent heat direct. Then you need to calculate that from the pressure. then you have to use your steam table to do that. All right, then the last part now was the most complicated part for most of us here, because the way the question was asked here, it was something else. They are saying, if some of the fuel heat is further absorbed by the dry flue, in this case, we are talking about dry, which is exhaust gases, calculate the available heat value. So we are asked on 6.3 to calculate the available heat value of the fuel in megajoules per kg. So needed in megajoules per kg. Air temperature is, and the dry exhaust gas temperature is 230. So the air temperature is the temperature that is entering, which is T in or T1, which is 36 degrees Celsius. And we've got T2, which is T out at the exhaust. That is where we have got our output temperature of 230 degrees Celsius. Take the specific heat capacity for exhaust as we are given the specific heat capacity, which is 1,045 kilojoule per kg degrees Celsius, meaning it's taken per temperature in degrees Celsius. All right. So in actual, we are dealing with the products and the dry exhaust gas, meaning to say whatever that we are supposed to work with in this case is supposed to be from the dry products. In this case, we are supposed to be dealing or to be working with dry products. But is it affecting our available heat value? All right, let us check the formula that we are going to have in this case. Let us go back to our formula sheet so that we do not act as if this is from something else. Do I have a formula that is giving me this one? All right, so here they just gave us this one for the higher value then, all right, which is fine. So let me explain it. I do not have the other part. I do not know. I'll check on the other part if we have got that formula. I just wanted you to see from the formula sheet so that we will be together. But in actual sense, the formula is supposed to be the available heat value is given by the formula. The available heat value is given as the lower heat value, which is the lower calorific value, the one that we calculated before, the lower calorific value, which is the lower heat value, minus the mass into the specific heat capacity times the change in temperature. Since our specific heat capacity is taken per kg degrees Celsius, so meaning to say the change in temperature must be in degrees Celsius, T2 minus T1 or T out minus T in. Since the answer is needed in megajoules per kg, it means our lower calorific value should be in megajoules per kg, as we saw that our answer was in megajoule per kg. So it also means our specific heat capacity should be in megajoules per kg. This is kilojoule per kg, so this must be converted to megajoule per kg degrees Celsius, meaning to say we are simply going to divide this by 1,000 to convert to a megajoule per kg degrees Celsius. All right. But the question is, on the specific heat capacity here, not on this M. The question is on the M now, which is the mass. Where are we going to have this mass? Because we are not having this. They are referring to the mass of the dry products, meaning to say we are supposed to go back to our normal calculations. How are we going to obtain the mass of dry products from the information that we are given? In order for you to have the mass of dry products, we are going back now to the inputs in this case, which is our carbon, hydrogen, sulfur, oxygen, this part that we are given. We know that we can obtain our products. In this case, we can have our products from these, whereby we all right, so this was, you're supposed to calculate it aside. So let me just use this space here for the products in order for us to have the products. So I'm just gonna use this portion. All right, since we are to work with the and it's not just the products, but it's dry products that we are working with. And dry products, that's where we are talking of carbon dioxide. Water is not there. Water is it's a wet product. We're gonna talk about sulfur dioxide since we have got sulfur. and the part of air which is our nitrogen in this case. We do not have the excess air, so we are not going to talk about the excess air in this case. So these are the only products that we need to obtain their mass, the total mass. This M that we see here is the mass that is going to correspond to the products in this case. And we are told that they are dry products. We're talking about mass of what? Of the products of combustion, the products of combustion after the combustion has taken place. That is how we are given the person here. If some of the heat, some of the fuel heat is further absorbed by the dry flue, which is exhaust gas. The exhaust gas we're talking about, these are the products of combustion. Combustion has already taken place. So that's why we have to consider the products in this case. So these products of combustion, as we understand from our theoretical mass, we talked about this formula. Let me just present it again for the benefit of revision. We talked about this formula for calculating the theoretical mass of air, since we consider having the mass of that is going to affect carbon to obtain carbon dioxide, hydrogen to obtain water, but we are not considering this on our products. Sulfur is going to be there. So this is the formula that you're going to take for our calculation now for the mass of air. Since we are going to need nitrogen, remember nitrogen by mass, this is taken by mass, and we know that nitrogen consists of 77% by mass, which is the percentage, the volume of, the percentage that nitrogen consists or as part of air. It is 77% by mass. By volume, we are talking about 79%. So meaning to say we are going to need that formula in order for us to have the nitrogen at the end, also to calculate our carbon dioxide and our sulfur dioxide. So we are given that the theoretical mass of air is given as 100/23 times the mass of oxygen, which is the mass of oxygen given as 8/3C plus 8H2 plus sulfur minus O2, like this. All right. So from this, I explained before, guys, what each part represents. So I'm not going to take much time to talk about to explain this. Let us substitute our values. So M is equal to 100/23 into 8/3 times the percentage of carbon, which is 0.85 plus 8 times the percentage of hydrogen, 0.07 plus sulfur, this is 1 kg oxygen. So it's going to be 1 times the percentage of sulfur, 0.06 minus oxygen, which is 2%. So 2%, that is 0.02. So that's M is going to be 100/23 into the mass of oxygen. So simplify this whole part here. This is the mass of the total mass of oxygen. So the total mass of oxygen there was going to be 2,86666, and so on and so on and so on. All right. So that's the mass of what? Mass of oxygen. So we can just use the value direct on your calculator, multiply by 100/23. You obtain the mass of air, which is the theoretical mass of air, which is 12,464 kgs. This is taken a kg fuel in this case. This is taken at a kg fuel. We do not have excess air considered in this case. So since we do not have the excess air considered, that means therefore this mass that we are seeing here is our mass of air. This is the actual mass of air, which is 12,464 kgs, because we do not have excess air. Remember, the purpose of calculating this is so that we can obtain the total mass of our products. And on our products here, we are saying we are going to need carbon dioxide on our products. So let us calculate our products in this case. So we need the total mass of these products. And on these products, we've got carbon dioxide, which is taken from the formula. Carbon dioxide, we need 8/3, which is 2,667 kgs of oxygen per kg fuel, per each kg of carbon. So we are going to add 1 kg, meaning to say carbon dioxide, which is the product now, it's going to be 3,667 kgs times the percentage of carbon. Remember, carbon is at 0.85 meaning to say we are going to obtain the total mass of carbon dioxide, which is 3,117 kgs. In this case, we are talking about the mass. So we move on to the sulfur dioxide. In this case, according to sulfur deposit, we are talking about dry products, as I referred before, that here we are going to deal with the dry products as we are given. So this is the mass of products, but being dry products. All right, so water is not part of dry products. All right, so we are going to take sulfur dioxide on our dry products. Sulfur dioxide, we need 1 kg of oxygen to burn sulfur. So meaning to say 1 kg of oxygen plus 1 kg of sulfur should give us 2 kgs of sulfur dioxide. So sulfur dioxide is got 2 kgs times the percentage of sulfur, which is the percentage there was 0.06. Remember, it was 6%. So just for the sake of time, so this is going to give us 0.12 kgs of sulfur dioxide, and also nitrogen, which is the one that we are going to obtain from the percentage of air. That is the percentage of it is 77% by mass. So we are going to use this as 77% of the mass of air. Since we do not have the excess of air in this case, so that means we are not going to have any actual mass of air from no. We are going to use that one that we obtained from our theoretical mass, which is in this case was 12,464. So that is going to be 12,464 kilograms. So this gives us the mass of nitrogen, which is going to be 9,597 kilograms. So that is the mass of nitrogen. So these are the products that are required. So what is the total mass? Because the whole part of our calculation is to obtain their total. The carbon dioxide here, the sulfur dioxide, the nitrogen together combined, what is going to be the total of these masses that we are given? So we are going to obtain a total of 12,834 kilograms. So this is going to be the total mass. With the total mass that we are having here, we can be able to calculate now the value that we are being acquired to, which is the available heat, the available heat value. And we said from that, since here we've got the total mass, which is M, we are now, these are the dry products. So now we can substitute from our formula, because we said in order for us to have the available heat value, we are going to need the lower heat value, of which we calculated this before. Remember, in megajoules, our value here was the lower heat value, this one, the lower calorific value, which is 34,498. So we're going to take that value. So our value is at 37. That's so 37 or 39. Sorry for that. Let me check again. 37. All right, 37. So this is 37. So the value there is at 37,498. All right, 498 minus the mass of the products, which is the dry product, the one that we calculated here. So remember, on our calculation, this whole part of our calculation, it was to obtain the mass of the dry products, which we got here as 12,834 kgs times the specific heat capacity, which is supposed to be in megajoules per kg. And I said anything in kilojoules per kg to be converted to megajoules, we are going to divide by 1,000. So it's going to be 1,045 kilojoules over 1,000. Now it's in megajoules per kg, per kg degrees Celsius. So that means we can multiply to the change in temperature, which is simply T out minus T in degrees Celsius, because this is taken per degree Celsius. So we are going to change, we are going to use these values in degrees Celsius. That is 230 minus 36, like this. All right, so that was going to give us the answer for the available heat value in this case. All right, so meaning to say, if you are to simplify everything from your calculator, your answer in megajoules is going to be 34,896. Automatically, this is in megajoules per per kg, as we were using our values in megajoule per kg. So that is how our questions sometimes might be, where you need to play around your formulas. As you can see, we need to play around now with our formulas. What are we given? What are we not given? And how can we obtain what we are not given but needed on the formula? Because the formula needs the mass, and the mass of the products. We have to go back to our theoretical calculations there. We only focus on the dry products in this case. If they just say the products, meaning to say water is supposed to be included. If there is excess A is supposed to be included also. So you work with what you are given. What is the question about? What is the question about? That is how you simply attempt these typical questions on the combustion of fuels, and also the calculation of heat value.